Okay, I see that people are entering from the waiting room. So I will slowly start talking because I see this. Okay, everyone is in from the waiting room. Welcome. I see that the recording has started. And where are you? You are at the monthly joint ESIP IT&I Tech Dive and CDI Tech Stack collaboration area call. And today our topic is Amazon Web Services for Research, Stepping into the Cloud. We're very happy to have invited Scott Friedman here from AWS to give us an overview and some discussion points. So Courtney New is going to give the introduction. Before we do that, just a few logistical things. We have the chat available for questions during the call. So go ahead and you can type questions in as they come up to your head so you don't forget them. And then at the end of the call, I will help to make sure we get to as many questions as we can. And do I have anything else? I don't know. My name is Leslie Shee, and I'm sort of an interim person here. In a couple of months, we will have Dave Blodgett from the USGS helping to facilitate these calls. So I'll look forward to that and forward topics to him. But for now, I am going to turn it over to Courtney New to introduce today's speaker.
Thank you, Leslie. So I'm Courtney New, and I'm part of the Cloud Hosting Solutions program at the USGS. If you aren't familiar with us, we are the required, supported, secure cloud offering for the USGS, and we provide on-demand computing resources and services in the cloud using Amazon Web Services, also known as AWS. So we have Scott here today from AWS, and he is going to present on AWS for Research, Stepping into the Cloud. In his talk, Scott is going to discuss a hybrid approach to supporting cloud and on-premise resources and how that can enable and accelerate research better. Scott has an extensive background in advanced research computing and currently focuses on helping university researchers and their institutions understand how to most effectively leverage AWS technologies and capabilities that enable state-of-the-art computational, data science, and artificial intelligence / machine learning research. I'm very excited for this educational opportunity. And with that, Scott, I'll hand it over to you. Thank you.
Can I make sure everyone can hear me? I think so. Thank you for having us today. As Courtney said, I'm going to talk about using AWS for research is what I spend my time doing. I'm part of the AWS higher education research team, although the higher education part is a little bit over indexing on what we focus on. Of course, we focus on research across nonprofits, government, higher education, and the commercial space. My group focuses primarily on the public sector side, so higher education, nonprofits, and government, which is what you guys are. My experience, though, is primarily as the CTO for Advanced Research Computing at UCLA. I was there for about 25 years, supporting about 15,000 researchers, faculty, postdocs, professional staff, and not including graduate students. And for about the last 2.5 years, I've been with AWS, basically doing the same job I was doing at UCLA, which was focusing on research enablement. And I like using the term research computing. In the past, we've kind of over-focused on HPC, although that's a big part of it. Research computing incorporates a lot of other types of computing and storage, and among other things. So I like to take a little bit broader picture of it, and hopefully we'll do that today. So really what this talk about is why. Why should I even worry or bother with the cloud at all? Research has been going on for a long time, particularly in your fields. We have clusters, we have workstations, and they seem to do the job. And along comes the cloud in the last 10 or so years. And, why should I bother? So really what this talk about is a little bit about, ways to think about the cloud to kind of begin to answer that why, why should I consider the cloud for my work? Do I, and when to a degree, should I use the cloud? And if I should, or I think I should, what are ways that I can take advantage of it? So I always like to start up with this picture. This is the laptop I used when I was a graduate student, many moons ago now. And at the time and it was missing the keys back then. This was my world, right? I was writing simulations on here. I was doing testing on here. I was writing papers or my dissertation even on this thing. And at the time it was a real expensive, powerful laptop, and it did the job. And one of the things I noticed was over the years that this was something that, as I used the term before, this was my world. So whether it was this or I had a small cluster that I used in my lab in the 90s, and that was how I saw problems. I saw them in terms of what I could accomplish, whether it was on this thing or something that looks like this, right? So when I needed more, I started building things like this. And I'm sure many of you who've been around a while, either use something like this, built something like this, or maybe even still have something like this sitting around, or you went through this at some point. And that allowed you to scale up what you were doing. Scale up either in terms of, vertical scaling, we're able to tackle bigger problems, or scale out. I could do more of them. Eventually, you get to things like this. These are obviously real systems. They're real photographs. That some of them are probably still running someplace. And, this took things to the next level. And that was fine also. If you're really fortunate, you have something like that. But the problem is these were not so fun to run. They were fun to put together, right? They solved a problem. Wasn't so easy to keep them running. And, maybe this is less the case in your world at USGS, but in an academic environment, and all of you spend time in an academic environment, people come and go. And I have to tell you that I had to send engineers out to labs basically every week at UCLA to go fix one of these things, or to, update them or keep them running. And that became a real problem for us and for the groups, because I didn't have unlimited resources to help them. So then, you get to something bigger. So here I use the word campus, but it could be your institute, it could be the agency, whatever you want to use. And some places have huge systems, some have smaller, some have multiple systems. These are, what we used to call a supercomputer. Most of them are shared resources these days, many people running on them simultaneously. Fewer and fewer run as so-called throughput systems, where it's just one person running on the system. Most of the big government meaning the national lab systems, run that way. You may have some systems that run that way because the problems are large enough that really only one person can run on them. But usually there's a mixture. And that, again, totally fine. And my message to everybody is, if you've got that and it's available to you, use it, right? As the little meme there, problem solved, or really is it? And I think that this is where I like to show this graph. This is a real system that's approximately the size of the picture I just showed. It is not any of your systems. It is not any of the systems I was responsible for at UCLA, but it's a real R1 university big cluster. And you'll notice probably, or already noticed right away, there's a giant Grand Canyon in the middle of that graph off in the second week of earlier this year. And you'll see that, something happened there. And what happened is nothing terrible happened. They just took the system down for maintenance. And for that week, nobody was doing anything. Otherwise, at least from my perspective, 72% utilization of the CPUs is pretty decent. My bosses would be happy with that at UCLA. I will brag to say we did a little better than that. But the point is that it's a busy system. And from an institutional perspective, this is fantastic, right? It's like, oh, everybody's busy, everybody's working. Yeah, we got to take the system down a couple times a year. All good. But from an individual or group perspective, this can be a problem, right? What if I need to, do something that second week, or I have something coming up in week 3 or 4? This can be a problem. Another, oops, let me click. Another issue is this. This is the same system, same time period. Again, a busy system. If you look very carefully, you can see along the bottom, there's a green line. Those are the number of running jobs, okay, that are running on the system. So exact time periods. So this is a busy system. It's running about, 25,000 to 30,000 jobs, sometimes bumping up a little higher to 50. But you'll notice the blue line are the pending jobs waiting in the queue. So any of you who've ever used a cluster know you submit jobs to a batch queue, and that scheduler does the best it can to make sure that it schedules jobs fairly. The problem is if there are too many, you get a lot of backups there. And you see this is a very spiky environment. So even if the system is up, right, that second week, there's a gap there still. But you can see that if you're unlucky, because this is essentially, you don't know what everybody else is doing at the same time as you, you're going to wait. It's going to take time for your job to schedule. And it's really difficult to know when your job is actually going to run, even if the system is just your groups, right? We had many smaller clusters, and the groups tend to all be working on different projects, and you can run into the same kind of problem. Not the end of the world, but if you need to get things done, you need to get things done. Or if you need to run a large job, or say a large distributed job, and other people are running smaller things, it can take time for the scheduler to gather all the resources to execute, a big distributed job. So, again, is that a problem? I will just say that the single most common complaint / question I used to get was, when is my job going to run? Right? Meaning, if you didn't really care, you wouldn't be asking the question. But you look around on most FAQs for clusters, that's usually pretty high up on the list of, why isn't my job starting? So everything's fine in your laptop or a workstation until it isn't. Everything's fine on a lab or cluster computer until it isn't. Particularly, aside from the things I just mentioned, you want to run an interactive application on a batch system. Yes, there are interactive nodes, and yes, you can tunnel, X onto a cluster. You can do all these things, but more and more researchers are not coming with the expectation that they have to, do some of these, frankly, more complicated things to get some of these things working. Accelerators, by that I mean FPGAs, or of course GPUs, or even other specialized processors. These are becoming more common in the sense that tools are supporting them, but getting access to them can be pretty difficult, or it's even more limited. Long-running applications, I mentioned that a second ago. A lot of shared systems limit how long you can run jobs. If you need to run something even longer, that can be a problem. I had many people come to me asking, I want to run a database, I want to run a portal, right? I want to share what I'm doing. A lot of the traditional research computing resources don't easily support those things. And of course, we mentioned the waiting. So what are the observations here? The observation is research computing is bursty, right? It's bursty in the sense that it's bursty from an individual perspective, tends to be, and it's bursty from a group or even institutional perspective. And, from the institution's point of view, it looks like we're having excellent sustained usage of the system. And the reality is the system is just simply under-provisioned. And there are good reasons for that, right? We don't have unlimited money to spend, and unlimited, we can't build an infinitely large system. But I think often there's a disconnect between the actual patterns of the way people work and the systems that are built to support them. So what can you do about that? So this is where something like AWS comes in, and how do we support that? So one of the ways the cloud is pretty amazing is you can adjust compute and storage, as a matter of fact, dynamically. So in this simple example, we have kind of morning, afternoon, and evening. In the morning, the time periods could be Monday, Tuesday, Wednesday, right? Or January, February, March, or whatever you want it to be. The point is, in the morning, we only need, and we don't have to get too caught up in the architecture of this, but these orange squares, let's just call them compute nodes, we only need 6 of them. And that's all we need. And later in the day or the next day, we need more. And I can't do the math here off the top of my head of how many there are, but there's a lot more. And we're only using those while we're using them, or maybe even for a particular workload. And then at night, we all went home and we're done, and it's all gone, right? So there's no managing it. There's no paying for it. There's none of that. It's just, we're finished. So as I like to say, Goldilocks for the win, right? You can get, if you need hot, cold, medium, that's available. You can scale things to be just right for the job that you're running. Another is they can be fit for purpose. So one of the challenges we had, I have another slide of that system that I showed earlier, and it shows how they overcommitted memory, meaning they bought twice as much memory that any of the jobs are using. And, that's an easy error to make. You don't know what the resources or the optimal resources are going to be ahead of time. You have to, make a best guess. I spend a lot of my time doing that. Here in the morning or, on Tuesday, we're going to do compute, and we're going to, C5 is just a certain type of instance we have on AWS. It's a Intel Skylake system. And here you're using 6 of them. And then later we're done doing the computation, and now we're going to do a visualization. I toss out the C5s and I create the system built out of P4s, which are systems that have a GPU on them, or a GPU that can be used easily for visualization. And I create the visualization. And in between, I've dumped the output of the computation into some storage. In this case, it was object storage on S3. And as I say here, you can dial in the specific type of CPU even further, like number of cores or the amount of memory that you may need on top of this as well. So again, we can build systems that are fit for purpose and tie that into what I just showed you of, time of day, or maybe I need 1,000 compute nodes to do the compute, but I only need 6 to do the visualization. So that can happen. So as I like to say, be the snowflake, deploy what you need when you need it, and then move on. And then finally, in the cloud, everything can be essentially ephemeral. So when you're done, boom, it's all gone. And all that's left here is the storage that's storing that data, or maybe even just the image of the output of the computation and the visualization. And by using infrastructure as a code, that whole infrastructure could be spun up again as needed. If you are interested in reproducibility and all these other kinds of things. So again, not using, not paying, right? You're not, generating carbon emissions. You're not doing any of that stuff, right? The money is not going out the window if you're not using it. You can shut it all down and get rid of it. And finally, of course, you can have availability, compute and storage on your schedule. So when you need it, you spin it up and you do what you need to do. You're not dependent on a shared resource any longer. Now, obviously, if you have a shared resource and it's available, and these other concerns aren't so important, or you don't have a deadline, or it doesn't matter when it runs, as I said it earlier, use it. Absolutely use it. So this is not a binary choice between what you may be doing today and using the cloud. I think that they both have their place. So as I say, you can skip to the head of the line. And I say you don't have to know anyone, because I used to get emails from professors saying, I'm special, Scott, bump me to the front of the queue, which of course I never did, but unless they were super special. So with the cloud, you can always be at the front of the queue. So what does compute look like in the cloud? So on the EC2 side, what we call EC2, which is elastic compute, this is what most people think of the cloud. This is virtual machines, bare metal machines even, and accelerated computing. So systems that have GPUs, FPGAs, Now we have machine learning, both training and inference processors that are, dedicated to that kind of thing. And then also now we have quantum devices that you can access in the cloud as well. So there's a wide range of not only within CPUs, you can use ARM processors, AMD processors, Intel processors, there's multiple generations of them. So pretty much whatever you want is available in the cloud. The other thing I'll say about this is we're generally at the front of the line. So if you order whatever the brand new NVIDIA GPU is, unless you're going to buy a truck worth, you're probably going to wait some time to get it. Usually we have them available very close to when they're, available. So if you want to be able to just jump on the bandwagon, you can do that. And you don't have to worry about a year from now when it's now out of date and you're still using the last generation's GPU. The other types of compute paradigms we offer are basically container-based. There's a lot of acronyms there. ECS is our version of a container orchestration service. What I like about it is if you're not an expert in Kubernetes, it's very simple to use and understand. It's also free. EKS is good old Kubernetes. That takes the usual amount of effort to set up and run, but you could do it in the cloud. In fact, you can even do it hybrid between the cloud and your local environment if you want. And Fargate and Batch are kind of higher level services for executing containers without worrying so much about the infrastructure. And Batch is a cloud native scheduler. And I'll come back to Batch in a minute. And then many of you may have heard of kind of the serverless model, where you're basically operating at the functional level. And our version of that is called Lambda. And it can be a very interesting way to rethink how workflows work. And even doing some scientific computations, there's been some interesting work there on how you can take advantage of serverless computing. I'm not going to spend any time on this. I kind of talked about this a second ago. Actually the numbers, I show 300 plus instance types. Instances are the configurations that are available to you. They're actually, I think, close to 400 now, and that number just keeps growing. But any kind of combination of things that are interesting to you, you probably are going to be able to find it in our warehouse of different kinds of compute. One thing I didn't mention a second ago is networking. You see here that currently we're up to 400 gigabits bandwidth with low latency. So many people like to tell me that AWS does not have InfiniBand, and that's true. But we do have something else called EFA, which is essentially as fast or faster in some cases, depending on the type of workload you're doing and the type of data sharing you're doing between the nodes. And if you're curious about that, I'd be happy to chat with you about it offline. How do you pay for things in the cloud? So this isn't like you cut a big invoice to one of our hardware vendor friends and a truck shows up and you install everything. As we saw a minute ago, you use things when you need them. And the most common way is on demand, meaning right now you go onto AWS and say, give me this, and a few minutes later it's up and running. And you use what you want, you pay for it, and there's no commitment. So if you have very spiky workloads, this may be the simplest way to and most cost-effective way to leverage the cloud. If you know that you're going to have a sustained usage, we have something called a savings plan. You don't even have to prepay for this. There are different discounts depending on how you do that. I wouldn't do this unless you knew you had a steady state compute load that was going to be running, and you could mix that with on demand for when you spike above that. And then finally, we have spot, which is a kind of typical or kind of auction market where you say, I'm willing to pay this much for this resource. And if we have resource available that no one's using, you often can get that for significantly less cost. So here the slide says 90% cheaper off of on demand, and that can happen. Now, if it's a much more in-demand type of instance, it may be less than that, or it may not be available at all. So one thing one needs to do with spot computing is to be flexible about the type of compute instance that you were interested in using. And this is a great chart, and I'm going to kind of reinterpret this a little for this talk. This is how we say, this pink level at the bottom is where you'd use a savings plan that's kind of steady state. The blue or purple is on demand, and then the green is for spotlight workloads for, like very short-term kinds of things. What I'm going to suggest is one way to think of this is the pink level could be on-prem resources, right? You have this steady state of what you're doing, and you have this resource, it's available to you. Either it's a sunk cost, you've paid for it, or it's very inexpensive and subsidized in some way or multiple ways. And the cloud then becomes this middle layer or the spot layer when you need to break out of it, either because you have a time issue or you have a capacity issue or both. And that's a way for you to take advantage. So this could be, the term that's used often is bursting. It doesn't need to be bursting, right? Like literally off of your on-prem system. It could be, and we have a lot of customers who are doing that. But it could just be using the cloud directly. It just depends on the type of workload that you have. Some of the things along the bottom there are some of the tools and capabilities that are around this. The most interesting ones are the two on the left, the auto scaling and fleet. These are ways of managing, if you're bringing up a cluster, you're bringing up a large workflow of managing multiple instances at the same time. It's just a set of tools that makes that easier to do. And again, this goes back to this kind of automation. Automation and the cloud go hand in hand. It's really something that one needs to take advantage of. And my recommendation for researchers is to use tools that do that automation for you, so you don't have to become a cloud engineer. Another question that comes up is related to that about not becoming a cloud engineer is how do you avoid complicated? It's like, okay, I understand I can get a computer, plug it in the wall, log into it and start working more or less. The cloud is this whole other thing. I don't know anything about virtual machines. I don't want to know anything about it. How can I do this? And if you're research IT, the question is, how do I make it easy to deploy these things for my customers or users? And I think there are a range of ways to do that. On the one end, that's probably the most similar is something we call parallel cluster. This is if you just want a good old Slurm cluster running on AWS, and you have scripts that submit jobs, and you want to use SPAC, and you want to use all the kind of environment or modules that we're all used to using and run MPI. Parallel cluster is what you want to do. And literally in 10 minutes, you can have a cluster set up in the cloud. Again, what's cool about parallel cluster is it does not allocate any resources except for the head node. Your partitions are defined to use whatever resources we have in the cloud. As I said before, I could have a queue full of AMD processors, another one with Intel, one with GPUs, so on and so forth. And those resources only spin up when a job is submitted to the queue and executes. And if there are no more jobs in the queue, those resources go away, and parallel cluster takes care of that for you. So it's kind of the best of both worlds, so to speak. You can have a familiar environment, but also take advantage of some of the things I mentioned before about fit for purpose and use it when you need it. There are many ways to run containers or serverless, whether it's Lambda or some of the container orchestration stuff. I actually suggest that if people are new to containers, container orchestration even, to start with ECS or Elastic Container Service. It's much simpler to use than Kubernetes. Kubernetes is all the rage, but you're going to go down a rabbit hole with Kubernetes. I think it's best to leave that to administrators who know how to run Kubernetes and take advantage of it, which you can also do on AWS. There are a bunch of open source tools. One that's floating out there that I always like is something called CloudNot. I'm not recommending you run out and try that right now, but CloudNot will take a piece of Python code, bundle it into a container for you, and then run it on AWS, and it will do all of even the containerization on its own. So you don't even have to know about containers to use something like that. For folks who need databases or portals and web presence, we have something called Lightsail, which is super easy to use. You don't even have to log into the AWS console. It's fixed pricing. So, you want to run a website or a database, you can do it for $8 or $10 a month and know that you're not going to have like a surprise bill. A newer area are applications and tools that are supporting cloud directly. So I'll come back to those in a second. And we'll also talk a little bit about machine learning and SageMaker Studio Lab. Before we do that, I just want to mention surprises. This inevitably comes up when talking to people who are used to doing research computing the traditional way on premises and stories they've heard about in the cloud. Somebody's got a big bill, and a scary bill showed up because they left an instance running over the weekend, or they went on vacation, or they just clicked the wrong button. And, how do you avoid that? And there are many, many, many ways to avoid these kinds of things. I was mentioning before we started today to some of the others that the tooling has become much smarter about this to help you avoid shooting yourself in the foot. The cloud is a very, very powerful set of tools, and with great power comes great responsibility. Frankly, I think that the tools should do better to help you manage some of that responsibility. And I think we have tools like quotas and permissions to keep you from turning on things that you shouldn't. Budgets and alerts, meaning you can set a budget, you can have it warn you that something is not what you expect. And then frankly, there are ways to shut things off, set it up so it shuts off, or use tool like parallel cluster, right? Parallel cluster will take care of shutting things down for you. So it's kind of hard to shoot yourself in the foot. If you're doing little tiny things, use serverless. It's very granular. Scale to 0, limit time. So this is an interesting one. This is not so much a cloud feature, but a scheduler feature, say of Slurm. If you have a queue and you can only run for 2 hours, well, you're going to limit your spend to 2 hours. And then scheduler take care of killing off, or, hopefully you've finished within 2 hours, but you don't have to worry about overrunning if the scheduler's taking care of managing that. And then finally, you can combine any or all of these with the spot market to even limit your spend even further. I mentioned parallel cluster. I won't spend a huge amount of time on it. Again, you can spin up a cluster literally in 15 minutes. I have another talk where I actually do it while I'm doing the talk. And, halfway through the talk, I'm like, okay, let's log into the cluster. And there it is. You can do MPI in the cloud. Using EFA, you can request instances that are physically close to each other. You concern about latency. You can select, pretty much any of the instance types that we have. It does work with the spot market. You can use either Slurm or batch scheduler. People who use batch for this tend to have more kind of cloud native approaches to their workflows. Most of the academic customers I work with and research customers are using Slurm. And those who are using SGE or other schedulers, are trying to move to Slurm. This is kind of always a good excuse to experiment with Slurm without messing up your current environment. And I'll just say lastly, SPAC is a fairly new-ish way of managing packages and tools. And with Lawrence Livermore, AWS has deployed a binary cache for SPAC on AWS. So you want to create a software stack on your cluster. It can be done very quickly directly from AWS's infrastructure. There's 3 ways you can deploy a parallel cluster, or 3 kind of approaches. One is a bespoke personal cluster. So you're sitting on your laptop and you can just boom, boom, boom. It's written in Python. So you set up a Python environment, create the cluster, it talks to the cloud, and then you could log in and submit jobs. Those who want to integrate with their on-prem, there's either bursting, which is integrated directly into Slurm, and Slurm takes care of, and we have a plugin that supports spinning up and down the nodes, and you can use your existing scheduler to manage that. And then a federated model, which are basically 2 clusters that understand what's going on both of them. And depending on your environment and how you want to do things, there are different reasons to do any of these. The simplest one, of course, is just to use the standalone approach. You can do all kinds of file. You want Lustre, we got that. You want NFS, you got that. You want SSD, we got that. Or object-based storage in S3. You can scale it up and down the IOPS. So if you need really crazy IOPS for your scratch, all of that stuff is possible to do. There's also a new tool called Amazon File Cache, which takes care of some of the data movement challenge with the cloud and on-prem. And that's fairly new. And they're adding capabilities to that all the time. And one thing that comes up always is egress. Most researchers are able to get an egress waiver from AWS. I'm not sure how if that applies to you guys, but it's worth looking into. It's a pretty generous waiver of the egress charges for moving data out of the cloud, short of having like a direct connect. So earlier I mentioned tools that are starting to support the cloud natively. Yeah, egress for everyone. I'm 100% behind egress for everyone. I think, and I imagine someday maybe we'll get there. But all I can tell you now is that Scott is advocating for that internally. We'll see. We'll see if I get listened to. We have these platforms as a service. So Rescale is an example of an engineering code where they have deep experience running engineering codes and a variety of research codes, not just engineering. That's where they started, CAE and things like that. They, can take care of a lot of the nitty gritty of getting clusters and tools running on the cloud for you. It really just depends on how much support you have. If you have local support for doing this kind of thing, then, they're of less use. If you don't, they could be of great use. So it's good to know that there are companies like this that can support that. Then at a more granular level, I have this tool called Coiled. Coiled is a company that was started by the guy who created Dask. So Dask is a distributed computing model for Python. It integrates pretty well with things like pandas and NumPy and the rest. And with Coiled, basically you can take a Dask application and extend it into the cloud to scale it into the cloud almost with no code changes at all. So I think that this is an example where a lot of tooling that people are using every day is starting to become cloud aware and cloud capable. And it's good to be aware of that. My favorite current example is MATLAB. Most science and engineering people at some point or another, cross paths with MATLAB for better or worse. What's interesting about MATLAB is they've created something called Cloud Center, which allows you to create a parallel pool directly from your laptop. So this is really interesting where you'll see here, this screenshot was from so you can look there, it's Friedman at UCLA.edu. I'm using my UCLA login at the time. And I created a pool with 240 workers on it. My Mac does not have 240 cores. And I was seamlessly able to create and run a job that required, well, not quite 240, but over 200 workers to speed up. And I was able to set this up within 5 minutes. Now, of course, I had an AWS account already, but the point is this was something that was trivial to create. And the other cool thing about this is, again, when I'm done executing, using those workers, they go away. The whole thing goes away. So it's only, up and running while I'm doing it, and it goes away automatically. And again, this is where the tooling is doing a nice job, doing a lot of the orchestration for me, where I don't have to worry about how to do that. Here's Lightsail. I mentioned this. This is a very, I don't know how many of you have logged into our console, but I will admit that it can be migraine inducing, and it's a little hard to know where to start or where to go. But for things like websites, data portals, things like that, and databases, Lightsail is really something everyone should take a peek at. I would not use this for computing. The instances they use behind Lightsail currently are pretty not our most powerful. But I will say that if you created a data portal, you can link Lightsail instances back to your main accounts or to much larger data stores, say in S3 or other place, or back on prem if you wanted to. So this is something that I think is people are under aware of. And I will hint that we have something coming early next year that's going to be based on LightSail that might also be interesting. Unfortunately, I can't talk about it yet. It's it's very painful not to be able to share that, but keep an eye open for something with the LightSail name in it. Storage. Keeping an eye on time here. So from the point of view of research, we all know it's growing, just like crazy. We're getting data from new sources all the time. We're getting all kinds of data. We also want to collaborate and share data. We want to collaborate while we're analyzing the data. We want to be able to share results and data that we collect for others to use. And, this is getting to be more and more difficult. I know it was difficult for me to address at the university, and I see it every day when I talk to researchers around the world now. And I actually think, the cloud this is another area where looking at the cloud through kind of a different lens than maybe you're used to is something that's worth doing. And I always like to joke how many, when I talk about data silos, how many USB drives are floating around. I don't know how it works at where you guys are, but I know at universities, these things are everywhere. And, who knows if they're even still working or people walk off with them. This is sort of my ultimate nightmare for a data silo is a USB external drive. I went into labs where there were whole shelves full of these things, bigger than this, but nobody really knew what was on them anymore or what was on them or even if the USB drive worked. So, we have this kind of notion of a data warehouse. The example on the left is maybe more of a traditional enterprise, data warehouse, but we could call this, we had a multi-petabyte storage and all kinds of research data on it. And, unless you had access to the systems that mounted that, you didn't have access to any of that. But nowadays we have data coming in from sensors or the web or devices or instruments or computational, output. And a lot of it is still going into some kind of a silo. And a lot of what we're trying to get people to think about is the term, we've actually kind of moved on from the notion of a data lake to something called a data mesh now. And, this is where a lot of this data can be placed and the analysis can be done by pulling data from a lot of different places at the same time. This could be useful for more advanced or more interesting analysis, combining different data together. And the point is it's stored in a way that it's straightforward to combine these things. It isn't a lot of data copying anymore. It's like, oh, Scott's got this data set. I'll make a copy of it. It's available all in one place, so it can all be brought together in a more efficient way. I like to show this. I use this little animation I'm going to show you for something else, but it's also useful here. So, research typically has, these are physical limits. So, I have 4 circles here. I have people that are sometimes they overlap. We have the little microscopes, which you can imagine is some kind of instrument, compute and storage and data. And a lot of it is, like I just described, I've got to, ask Bob for the data and I somehow copy it over into something I can use. And, that's worked. What's interesting about the cloud is you can have a different structure where basically you're virtualizing access to things. So again, the instruments are going to be where they are, but collaborators, or if you're, on a sabbatical or working from home, like a lot of us have been doing the last 2 or 3 years, we can give access to different data sets as needed. If you have people coming and going or temporary collaborators, this becomes a much more tractable problem to solve. And, the boxes at the bottom, I list them as AWS, but they don't necessarily, those may be in the cloud, but there's no reason why the office can't access Lab B remotely, and that can be done securely and safely, and, whatever rules need to be followed. Those things can be managed in the cloud often much more easily and consistently than it can be done on-prem. And I'm saying that just from direct experience of having to do it at a big institution like UCLA. Let's see here. Oops, what's going on? Oh, there we go. Now, in terms of data storage, the types of data storage, again, in the cloud, there's, whatever you need is there. You want object storage, which is kind of where AWS started with S3. You want block storage, which, you can put whatever file system you want on that attached to a compute instance. Then we have file storage. So EFS is basically NFS. And then we have some more bespoke types of servers. Now we support NetApp, Windows file server, kind of natively, meaning, the service appears as a Windows file server or a NetApp component. You can integrate that with an on-prem system. We also support ZFS now. And I think there's one other that I can't remember. And then we have, of course, Lustre for those who want big parallel storage capabilities. And all of these can be dialed in depending on kind of the scale, the bandwidth you want or the IOPS you want. There's some dials that you can turn. And in terms of moving data, of course, there's all the traditional open source ways, rsync and Globus and all those friends, Aspera, but there's some AWS native ones as well. And of course, now we have this file cache, which is another way to kind of do data movement in a more transparent way between, say, a local POSIX file system and, say, Amazon EFS. So if you had an NFS scratch space in the cloud, or even Lustre for that matter. I'd be remiss if I didn't talk about machine learning. Machine learning seems to have found its home in the cloud. There's an enormous amount of machine learning going on. I like to put this eye chart up just to give you a sense of one thing, which is in the cloud, there's an interesting combination of low, medium, and high. So you can see at the bottom, if you're just old school and want to do things directly, using, all the, the common libraries that people are using for doing machine learning or data science in general, and you want to just put it together yourself, you can do that, okay? Above that, there's tools that kind of take away a lot of the infrastructure management piece. So, our main tool for that is the SageMaker suite of tools. We also support RStudio on there. There are many ways to run RStudio and other tools like that on the cloud, not just through SageMaker. But SageMaker offers a lot of higher level capabilities that, many people find useful, particularly if you don't want to be bothered with, setting up and managing infrastructure. And then above that, we have, these basically black box AI services that Amazon has created. Many of them Amazon proper uses more generally and have made available. They're in a wide variety of capabilities. Some are, as you see, core and specialized. The core ones are, things like speech to text, text to, text extraction from like handwriting and image analysis and all that kind of thing. And then we have some higher level ones that are more domain specific. It really just depends. I work with researchers who don't, they want to leverage a machine learning, but they don't want to, have to go spend a year learning about neural networks and deep learning and all the rest. They just want to try and take advantage of the capabilities that are there. And they can do that with those higher level services. And Amazon, like our competitors, has an army of people who are, researching and doing things in these areas, because as you can imagine, the company has a lot of use for it as well. If you're just dabbling in machine learning, I think that you can check out something called SageMaker Studio Lab, which is fairly new. It came out last summer. It's free. It's notebook based. So if you're a Jupyter Notebooks fan, you'll feel right at home. I will say that if you're not a Jupyter Notebooks fan, you can also, it's pretty easy to get something like Visual Studio Code running on there. You can run with CPU or a GPU. And did I mention that it's free? The sessions, I think the exact configurations of how long you can run a session, meaning you're computing something, have changed a little bit, but it's roughly the same. I think there's a window of time that those, like every 24 hours, you can use 12 hours of CPU, or I don't remember the exact setup, but these are legit systems that are running on. They're pretty performant, if that's even a word. And there's tons of learning materials in the notebooks that come up. So again, if you're getting started or just want to dabble in machine learning, this is kind of a no-brainer way to do not only that, but also get your hands dirty with the cloud. You do not need a AWS account to use this, meaning, it's free, and, you can log in just with your own personal thing, or, so there's no connection back to your official AWS account for this, right? So that's one kind of maybe downside. If you do,
excuse me, I just wanted to give a time check. There's 8 minutes left in the hour, so wasn't sure how much longer you have.
we're right at the end. So
Okay, thanks.
thank you for bringing that up. So anyway, this is something that I encourage you to check out if you're curious about machine learning, either in the cloud or with SageMaker, or just machine learning generally. The last thing I want to talk about is how we work with researchers. One thing I think many researchers, including folks like you, don't know is that people like me, and there are many others with either more specific knowledge than I have, or different knowledge, are available to you. We don't cost anything. We're not here to sell you anything, really. I mean, obviously we want you to use AWS, but we can engage with you on projects that you're working on if you're curious. And that means that, we do, and again, this is maybe a little more university focused, but, we do things like this, right? We come and share this perspective with you. We can help with proof of concept. So if you're trying to build a proposal for funding, we're here to help you. We can do that. You want to see how it might look in the cloud, we can provide credits to help architect a proof of concept to get a really tight idea of what the spending might look like. Once that, hopefully you do get funded, and I'm sure you would, we have ways of helping you with learn what you need to learn, or be there to help you do this the right way if you have compliance requirements associated with this, or other tools that might help do what you need to do, and ongoing kind of operational stuff. And again, it kind of circles back to continuing with training and advice. And I just want everyone to come away with this knowing that there are resources within AWS that you shouldn't be shy about reaching out and asking about it. We're happy to help. That's what we're here to do, and we need to do a better job letting all of you know that we're here for you to take advantage of. Open data, there's tons of data that you folks probably would be interested in sitting on AWS. It's free to access. You can use it now. Obviously, we prefer that you would use it doing compute on AWS, but there's nothing stopping anyone from using it anywhere. There's hundreds of petabytes of data stored here, and you can go to the registry and see what's available. And actually, I say 300 data sets, that's gone up even higher. And then last, I mentioned this before, we're here to support you. Please reach out if you want. We have credits available. I'm not a fan of credits in the long term, but if you want to explore the cloud and do a proof of concept, that's the area that we like to deploy credits, so that we can show you that the cloud is a viable approach to doing research. And with that, I will stop. So thank you so much. That is my email if any of you want to reach out directly, or go through Paul, who's your account manager. It's probably the best way to go. But if you have a quick question or technical question, I'm always happy to get email from people. And with that, we'll see if there's any questions before we run out of time. Thank you.
Thank you, Scott. Thanks for that overview, and thanks for the active conversation in the chat. This is a reminder, this is a joint call, so we do have a lot of USGS folks on the line, but it is not just USGS, we're joint with Earth Science Information Partners. So I put a little note there, do enter your questions, but we'll try to take more general ones first. And let me just go ahead and start with the one that Dave has entered here. Are there common patterns and anti-patterns of research teams and organizations providing enterprise level account management? So for example, big research universities or federal agencies, is there an expected number of admin support staff per research staff, for example?
Well, I think that depends on it goes beyond just AWS or cloud, right? It depends on, how much research enablement you do, I think. So at UCLA, we had a team of 45 people. But I would say half of them were dedicated specifically around research enablements, and some were researcher facing and some were infrastructure facing. So infrastructure means both on-prem and cloud. So they weren't normally talking to researchers. I will also say that in the cloud, the number probably can be ultimately a little lower because, again, you want to automate as much as possible. So say a landing zone that vends accounts. And the idea is, the way to think of it is the kind of the basic guardrails get deployed. Guardrails meaning security guardrails, what people can do and can't do, happens orthogonally from what happens inside of that box that gets vended to them. And then who works with the researcher to deploy, say a cluster or whatever their workflow is a separate action. And some researchers just want to do it themselves, and others, want a lot of handholding, and some want to engage on a more formal way. So the answer is it really kind of depends. But I think the main factor is how much engagement, are you just vending accounts and walking away? That's a much lower number, of course. But just, I'll give you, the numbers at UCLA. We had 10 PhD level research enablement people with different domain expertises. And that was for about a 15,000 faculty population. So, if you could do better than that, your researchers would probably love you. But we did the best we could with that number. I hope that gets to your question.
Okay, very good. Moving on to the next question from me. I do hear a lot of requests for training, people getting started for the first time. It's a very high, a lot of things to learn. So do you have advice on the best ways to get started and maintain updated knowledge for using the tools that you talked about to us today?
My advice is, first thing is you need an account. My advice is to reach out to us, actually, because I think one of the things that we can do the most is help curate what to focus on to start with. There's tons of training available on AWS's website that's free. There's some introductory things, and I can either point you to those to focus on. The bigger problem is what to focus on and what to ignore when you're getting started. And that's the biggest actual question that I get from a lot of people when I dig into it with them. So there are resources to help you get started. Like, I just want to spin up a VM, right? And have Ubuntu on it and run my code, right? I mean, that's where somebody just wants to start. And we can help point you to some resources that step you through that. So my recommendation is reach out and we can help provide and give you some pointers for that.
Okay. Thank you so much, Scott. We are at the hour. I was going to poke people like, where are your questions now? But we are we would like to be respectful of everyone's time. And I think I'm supposed to say something like this call has been recorded. It'll be up on the ESIP IT&I site. And I thank everyone, especially you, Scott, but for the people who attended and your questions. And we may have more discussions around this coming up, and we'll try to coordinate with our contacts at our various organizations. Any of the other co-hosts have anything to add?
Nope, this has been great. Thank you, everyone.
I'm sorry, go ahead.
I think Allison said thank you.
Oh, well, you're very welcome. Thank you for having me. And I'll just say that if you guys want, we can go through the questions offline, and Paul and I can provide some more answers that you can share out, offline.
All right. Well, with that, we will see you in the new year, 2023, for our future ESIP, IT&I, and CDI Tech Stack calls. Thanks so much and hope to see you at a future event.
Thank you, everybody.